Welcome to the last presentation in the series on integration of trig functions. And just remember, in this course we expect you to know a fair bit about integration from other courses, and we're just going to top up here with reviewing some of the ideas and extending them to trig functions. So let's have a look now at the fundamental theorem of calculus right here now, and see if you can remember what was happening there from the earlier presentation. The fundamental theorem says if you integrate from a to b across an interval, then it's f of b take f of a. Screen clippings here are from Hayes and Harris publications, so should have their textbook handy by. Oh, I just noticed a mistake here. That's around the wrong way, isn't it? It should be a at the bottom and b at the top. Oh, I should have noticed that before I clipped it. Okay, so it's f of b take f of a. And where did that come from? Do you remember? All these symbols are very important here. That means the sum, and we're making a whole total mass area under the curve by finding the limit as n tends to infinity, n tend to infinity of I equals 0 to n. This is the sum of areas, isn't it? An infinite number of areas of rectangles under the curve, and we let this be a symbol that representing a long skinny s, and this reminiscent of the height and the width of the rectangle. And the process being called integration. Let's go up here, making a whole solid mass as one across there. Do you remember all of that? Okay, so that's the idea. And the fundamental theorem of calculus, of course, is intimately connected to finding the area under the curve and between the curve and the x-axis. But not always. We better have a look at that. Okay, so what we're going to be doing is trying to evaluate that function across that the f of b, take f of a sort of problem, across this interval from 0 to pi on 6. And we need to remember that here, come down to the middle again, this f function, f dash of x, is little f of x. And that's the idea. To find this function, we've got to anti-differentiate or undo the differentiation and say, well, if that's a derivative, we've got to go backwards and find that function, which will be the area giving function. Remember that from the first presentation, hopefully. Okay, and then we're going to talk about whether it's going to represent an area, and then maybe can we work out the area between curves, or when it goes under the axis, what happens to that sum, the sum of an infinite number of rectangles, areas, what happens to that? We might have a look at that. Okay, so let's come down and just review all of that. And here we have it. fx is the integral, so this is the fundamental theorem of calculus, and the function's got to be continuous. So in other words, across the interval from a to b, so we might have something like this. There can't be any points at which it's undefined from a to b, wherever that might be. It's got to be continuous. Okay, no points at which it's undefined. Okay, and again, I've missed it. Coming from the textbook there, that should be around the other way. From a to b is f of b take f of a. Okay, so there's the correct notation there, from a to b. And that's what we're going to do. Instead of putting that, we're going to use this little notation here. We're going to get the integral, which we've been doing in the last presentation, evaluated at b minus the value at a. We're going to use this new sort of symbol to represent that going on. And here's what we say. It's the integral from a to b of fx with respect to x, and that should be the other way around. Sorry about that, I missed that. Okay, the function f of x is called the integrand, the thing you're integrating. A and b are the upper and lower limits. From a is the lower to b, so what we do is go across an interval, a smaller to b. Remember, we defined that area giving function when we were looking for it early on in the first presentation as the function which gives an area from a given value up to t, and we tried to work out using limit theory there what that function would be, and we found that its derivative was the original function, and that's where the big F comes from. Okay, remember, f dash of x is our function. Okay, the derivative of our area giving function is the function we can't start with, so we've got to undifferentiate it, or find the antiderivative if you like. Okay, what we've been doing is this, just finding things like the integral of x squared dx, and we've said that's x cubed on 3 plus c. That was practicing if we could undifferentiate this and find the f of x function. And remember, we had a whole family of functions which when differentiated back would give that function because the derivative of a constant is 0. So you could check that. This is called the indefinite integral because there's a whole family of them, nothing definite about what we've done there. There's a whole family. But when we go to finding the definite integral here, the definite integral from a to b, again that's around the wrong way, and evaluating it, f of b on the upper end minus f of a, this is a definite integral. There's no c's in it because if you have a look, x cubed would be b cubed on 3 plus c, excuse me, minus a cubed on 3 plus c. So that's f of b, take f of a, and they would disappear. So you come up with a definite fixed answer there because you're actually working with a particular function across that interval. You don't have the c problem there anymore. See how c's not a problem? Oh, see that? I hope you do. Anyway, all right, so let's have a look at some of the properties now. From other courses, you should know this, and that is the integral from a to a across under the function there, the integral from a to a. You're not going anywhere. So in other words, just keep in mind our interpretation of the fundamental theorem now. We'll go this way as well. So here, fundamental theorem, we're summing across an interval, let's say from a to b, of the areas of the rectangles, height f of x and width delta x. We're taking an infinite sum so that we can find the limit of that. Okay, so here, if you went from a to a, you haven't gone anywhere. So it's going to be 0 if you think about it like that. Integral from a to b, that's going from lower to higher, will be a negative of b to a. Could you have a look at that? A to b, the first one is f of b, take f of a, and the other one is f of a, take f of b, isn't it? Thinking about this going the other way around. And so 1, if you multiply this by neg 1, you do get that. So that's a simple one there. And if you have k times a function, go back and look at the first principles definition of the derivative, k comes out the front of that process, doesn't it? And so the integral of k times the function is k times the integral, as it is with the derivative. Check that one out. That belongs in another course, but we need to use these in this course in trig work. Okay, and if you integrate the sum of the two functions, it's the sum of the integrals across that the interval there. So you can split up a function like x squared plus 2x, if you wanted to, into the integral of x squared dx plus the integral of 2x dx. You could do that. Okay, and again, you've got to look at the definition of the derivative there to see how you can separate those limits into sums. Okay, what about this? Integral from a to b, got it right there for once, is the integral from a to some point in between, and then from that point further out. In other words, you can split the interval up. So over here, you could integrate up to m, and then add on the integral from m to b. Just remember, at this stage, we're working with a definite answer. It does not necessarily mean the area. We have to look at the graph to make sure the summing of the rectangles leads to all positives there. We'll have a look at that again in a minute. Okay, what about this dude here? Let's look at the process. First of all, finding the integral of this. Is that a function which is directly produced by differentiation? Yes, it is. The derivative of minus cos is sine. Derivative of cos is sine. Derivative of cos, is neg sine. So here, to get positive sine, we'll have neg cos. Just remember, integration of sine is unfriendly. You've got to put an egg in there. When you differentiate sine, it's friendly. Sine is cos. If you differentiate cos, it's neg sine. It's unfriendly, if you like, on differentiation. The integration of sine, however, going backwards, is unfriendly. It's neg cos. And the integration of cos is friendly. It's just sine. Do you get that? That's one way of trying to remember it. I hope I didn't confuse you there. So we're going to put these limits here now. So that's our setting out. which means we'll sub pi on 3 in and naught in. So we'll have neg cos of pi on 3, I hope you remember these, is a half, cos of naught is 1, so neg by neg is plus 1, so we get a half. Now we have not looked at the behaviour of sine x over that interval. We must make sure all our summing is of rectangles of positive height if we want to make an area implication or inference. But if we just want to find the definite integral, that's it, and we do not put square units because we haven't investigated whether that sum does represent the area. Okay, so the integral from 0 to pi on 8 of sec squared, is that a function which is produced directly from differentiation? Yes, we know that. It's tan 2x, but we must also divide by the derivative of this on integration. Reversal of the chain rule for a linear function in here. That's a function in x, so the integral of sec squared is tan, and then dividing by the derivative of this. Check it with differentiation if you like. Now subbing in 0 and pi on 8. Pi on 8 first, 2 times pi on 8 is pi on 4. Take a half tan 0. Tan of pi on 4 is 1, so it's a half, take a half times 0, which is a half. Okay, so there we have it. That's the answer to the definite integral. And look at what Hayes and Harris have got here. You should have their book handy by there. This is a TI way of finding the definite integral. So let's have a look at the Casio way of finding the definite integral. So there are two ways here. First of all, I want you to go to run mode. So this is run mode, one way of finding the definite integral with technology here. So highlight run mode, push execute, and you get to here. And then what I want you to do is to hit options. And if you hit options, where's options? In here. See that option key in there? Go in there, hit option, and this window comes up, and there's the one that you want, calc. So you'll hit in here F4, okay, to get calc. Come down to this window then, and have a look at what we've got, and there's a little dude in there. Okay, integral. So you'll hit F4, go in there, F4, and it comes nicely set up on this window for us to fill in the little boxes, and you scroll around the screen to those boxes using that key, and when you highlight it you put in pi on 3 naught and sine x in those posies, and then if you hit execute, there's our answer. Okay, so there's our answer to the definite integral. No implication for area yet. That is just an answer. When you're asked to find the definite integral, you follow that process rigorously, absolutely. Okay, find the function whose derivative is given there, and go in reverse, find the antiderivative, substitute in the two endpoints of the region, and away you go. Okay, let's look at another way of finding it on the Casio. This is using graph mode, and has a disadvantage and an advantage. So it's probably better to do it in run mode, but let's just have a look. You select graph, and here's our function, y equals sine x. We'll enter that, and then we will graph the function. Here we go, graphing it. I've graphed a fair bit of it here. Don't need to go that far, really. And now what we'll do is, again, choose options. So come in there to the options. Okay, and when we have options now, we get this window, which doesn't have what we want, so we've got to select the next window. So hit F6. Okay, and we're coming down here now, and the next window, there it is there, the integral sign. So you're going to hit F3 in there, go in there, and we get this window. It's asking us for the lower limit, so we'll enter naught, hit execute, it asks for the upper, we'll hit pi on 3, and then it does give us the answer. But hey, where is it? It's over here. There's a half, but what do you reckon might be the advantage of graph mode? Can you see it? It's actually shaded the area which that definite integral represents. Now we don't want square units, we weren't asked for that. We're simply asked for the integral from 0 to pi on 3 of sine x here. Okay, well, if we wanted to have an area implication, can you see by shading that in and no shading downwards, which would give negative heights, we could make an implication about area. I'm going to talk to you about that a bit later on. So probably the quickest way for just a definite integral is run mode. But be familiar with your calculator. It's a great tool. All right, come on down now and let's have a look at some for you to do, and I want you to check them with the calculator. We'll just come down there. Okay, so go through, remember the process in finding the integral to start with, and then the definite integral by subbing in. You need to work out, is there a function which when differentiated gives that? Can you check? No. Can you use a formula to change the function? Or is it coming from the chain rule? Have a look. Products are a bit suspicious. Are they from the chain rule? Or do they have to be simplified into separate functions which can be related directly to derivatives of particular functions? Okay, have your strategy. That's very, very important so that you can do that quickly. All right, let's go down and look at the answers now. Okay, so there's some answers for you. They're just values, remember? You're asked for definite integral, not asked whether they represent area or not. Okay, so let's go down now to another example. And here we go. And you can see here, the same question is going to come up. We've got to deal with this. Is there a function which when differentiated gives that? Well, it's a product. So we know we can't reverse the product rule. That's far too complicated, or the quotient rule. But we do get a product from the chain rule, don't we? And we did this in the last presentation. And the chain rule produces a chain of derivatives. Okay, so is that, will that qualify for coming from the chain rule? We'll try and reverse it. Yes, remember the test? That is the derivative of this little function in here. So this is a function of sine x, and there's the accompanying derivative of sine. So let's set it up to show that it's a chain rule. And that process is called method of substitution. So what do? You identify the derivative, and u is the function whose derivative is given there. So u is sine x. Please note, not root sine x. It's just a function whose derivative or near derivative is present. So you write that. Then, therefore, you can write that this is the integral from pi on 6 to pi on 2 of, put it all in u land. This is proving the chain rule pattern. And you can then say, well, we don't have to worry about the cos x dx, this part here, because we only have to reverse the u, the function in u, which is u to the half, and with respect to sine x or u as a variable. Look at this though. Oh, what's happened here? Uh-oh, yes. We're going to, if we stay in u's here, we've got to substitute x is pi on 2, the upper limit, into sine and get a u limit. And pi on 6, the lower limit, into sine and get a lower limit. So that's what these numbers are here. Very important to change the limits. People often make mistakes here. They don't do it, or they do it incorrectly. They don't do the substitution. Okay, so then we integrate the function, divide by 3 over 2, which is equal to, we'll put this here, u to 2/3 divided by 3 over 2 multiplied by 2 over 3, a half to 1. And then substituting it in and then simplifying it. So it gives you a nice exact surd form here, whereas on the calculator it will give you a decimal form. Okay, now I want to mention something here. If you don't like this, there is another way you could approach it. Start off with just the integral. Okay, so here, start off with the integral. Don't put any limits here, and then change it. So say it equals the integral of, get down to this level and go into u land. Come up with an answer. So this will be u to the 3 over 2, or 2/3 that, plus c. Then put your u back in, sine x to the 3 over 2 over 3, plus c, and then go back and put the integral from pi on 6 to pi on 2 of root sine x cos x dx equals integral from pi on 6 to pi on 2 of your function in x land. Don't stay in u land, okay? So we don't need the c there, and then evaluate it, etc., etc., etc. So if you don't like changing the limits, you can do just the ordinary integration. Don't put any limits on here. Go through and do it as you did before. When you've got the function, but don't forget plus c, then take that function through the definite integral process. So you've got a choice there. Make up your mind what you'd like to do there. All right, come on down and let's do tan 2x. So usual approach here, is there a function which when differentiated gives tan? No, don't get confused. The derivative of tan is sec squared. So you can integrate sec squared, but you can't integrate this one. Ooh, where did it come from? Don't know. We better apply a formula. That's our strategy. So the formula is sine 2x on cos 2x. And now we see, that's a quotient. That could have come from the chain rule. Why? Because we can think of this as 1 on cos 2x times sine 2x. And is one of these the derivative of the other? Or, well, either way, well, this is not the derivative of that. But sine 2x is minus the derivative of cos. So let's go to set it up and prove the chain rule. So we let u be what? The function whose derivative is there. And that's sine. Sine is the derivative. So cos 2x is u, not 1 on cos 2x. Just a function whose derivative is present. Then write down to u by dx is neg 2 sine 2x. Then we can write this in here from 0 to pi on 8. Don't change the limits yet. Of 1 on u neg a half. So up here I like students to divide by neg 2 so they make sure they substitute in correctly for sine 2x. I would rearrange it up there to find the expression for sine 2x so you can put it in this hole in here without error. So can you see you have established that this came from the chain rule? You are showing the chain of derivatives here. So you can take neg a half out the front, that's a constant rule, and then we've got to change the limits here. So this is what they've done up here. Substitute 0 in, or pi on 8, the upper limit, cos of 2x is 2 times pi, 1 on root 2, and put in 0, that's a cos of 2 times 0, which is 1. And then go through in u land. The integral of 1 on u is ln modulus of u, because ln is only defined for positive values or 0, and so we've got to put that absolute value sign in, and we go from 1 to 1 on root 2. So we've got to put 1 on root 2 in minus 1 in. Okay, and then we can simplify it at the end. ln of 2, the neg a half, is neg a half by ln 2, which with that neg a half makes a quarter. Just remember your log rules there. Okay, so log of 1, of course, is 0. Power you raise e to get 1 is 0. Okay, some rules down here. You don't have to put those in your proof. So that's interesting, isn't it? Just watch that. Remember, a quotient can be best looked at as a product on the way to possibly saying, has that been produced by the chain rule? Okay, time for you to have a go. Let's have a look at some down here. So here we are. Just remember, first thing you'll do with that is change it to a product, these here, and just check out whether it's come from the chain rule. Okay, so have a look at all of those. Now make a choice. What are you going to do? Are you going to go and change the limits as you go into use, or are you going to just integrate this function, come up with a function, and then do the definite integral part at the end? Your choice. Okay, pause it. You should do most of these. You need the practice. I'll show you the answers now. Okay. All right. Let's go down now and advance this a little bit to what we've been wanting to do, and that's find the area under the curve. Because that's where it came from originally, wasn't it? We said we're finding the limiting value of the upper and lower sums way back in the first presentation, and that was taking an infinite mass of rectangles, and the upper and lower sums converge on the limit of this if you take an infinite number of those rectangles. Okay, and this is the height and this is the width. And we said let the function, the area giving function, be A, and we found that A was such that A dash t was F, or here F dash t was F. We've gone to that notation now. So to do that, we have to find our f function by finding the antiderivative, undo that differentiation, and then evaluate it across the interval. It should work, and it does. Here we are. If it's positive and continuous on the interval, so no gaps, it's all above the axis, if you put in your f of x i's there and delta x's, they're all positive. So the area is given by the fundamental theorem. But look out, hang on, come down the bottom here, this example. If you summed across the interval here, so we'll just drop this down a little. So if we summed across here, f of xi, all of those are upside down. There's delta x. These are negatives. So if we sum those, we would have a total negative value. Okay, that wouldn't work. So we've got to check the graph because this represents the sum of an infinite number of rectangles areas there. If you look at it carefully though, it's coming from f of xi, the height, times the width, which is fair enough, but not down here where the height's upside down. So what would you do? You could take it away from 0, thinking of that as another line, or you could just say, I will integrate neg f of x. Okay, so I'll turn it upside down. We'll find another way of doing that in a minute. So neg f of x would make the function like that, so that the area would be a positive. Okay, so or we could put a negative out the front. So we're just adjusting the fundamental theorem a little bit. Okay, what about this one here between two curves? Well, that could be the sum up to there of which one's on top f of x and take away the area under g of x. So it'd be the integral of f of x, we won't write it there, it's written over here. Here we are, integral of f of x take g of x. Okay, if one is on top of the other throughout the interval. Think about what you're doing. It's a simple idea. It's an infinite rectangle sum, and you have to have your rectangle heights positive. By the way, you might like to prove, does this also work if we have, let's say, it under the axis, or partially under the axis? That's an interesting one. If that's f of x and g of x, the answer is it still works, but you might like to prove that. That really belongs in another subject. We're just using it here for trig functions. So across the interval from A to B, the area enclosed, you've got to find those points of intersection. It's the top one minus the bottom one. Does being partly under the x-axis have any effect on the validity of that? Well, the answer is no, but you might like to try and prove that. What about this one here, where f of x is on top in one region, that's there, and underneath in the other? So if we summed that rectangles here, it'd be f of x take g of x would make that positive, but here f of x take g of x is going to be negative. That one's under that one. So that wouldn't work. So what do? We split the interval up so that we're going to get positive rectangle heights here by taking the one on top minus one on underneath, and positive there as well. If you integrated just across the region, what would you get? That would be, let's call that A1, and this A2. This would come out positive, A1, but this would be minus A2 because the rectangle heights are around the wrong way. They would sum to a negative. And if you did it just across there, you would have the answer to that, and you wouldn't know. So you must, when you're using the fundamental theorem, analyse the graph and see what's going on. Don't blindly just sum, just integrate across the region of f of xi delta x. That's where it came from, remember. Just don't do that because it may not mean area absolutely there. All right, so interesting, isn't it? So we're going to do some problems in a minute, but I've got something for you here. Getting confused? Well, technology to the rescue. Here we go. What if we wanted to find the integral from 0 to pi of sine 2x? Okay, well we can see we've got to know that that's going to be a positive height for the rectangle is f of xi. And so if we went across there, that'd be all right. The definite integral would give us that sum and it would be positive. If we went across this whole interval here, these are down here now. That's a problem. So we would have to split the interval from 0 to pi on 2, then pi on 2 to pi of neg f of x. That gets messy, doesn't it? But what if we use technology? We could tell the calculator to make all of these lumps and bumps positive. Okay, and do you know the function that does that? And that's the absolute value function. So we could do that on the calculator. We can't do that by hand. So we're going to tell the calculator to integrate it straight across the interval. We don't care. We don't want to split it into pieces. We're a bit lazy. And tell it to take the absolute value. So it will actually make this lobe effectively positive, because the absolute value of this set of negative values here will be positive. Let's see how you do it with technology, because by hand we would have to say integral from 0 to pi on 2 of sine 2x dx, and that's all right, but here we're going to have to integrate from pi on 2 to pi of neg f of x to turn the sum of those negative rectangle heights here into positive. So we'll call it neg f of x. So that would be the graph of neg f of x, or neg sine 2x in that region. Okay, get your head around that. That's important. Okay, so let's have a look at the calculator. So again, in run mode, go to run mode and hit execute. So you're into this window, and then you've got to go to options again as before. It's in there, options, and choose the integral. So we're up to here. But now we have to do options again. What have I done? Oh no, I've done options again. Here we are in there, options again, and we get this window, but we need to have a look at in here where to find the absolute value sign. So here, go to complex, which is F3 in there, and here we find it. There's abs, the absolute value, as we did with complex numbers. So hit F2 and see it sits in there. Now we can start moving around with this button, filling in those boxes, and we get modulus or absolute value of sine 2x. And when we do that, we get the area across that whole interval is 2, without actually worrying about what the curve is doing. We're telling the calculator, make them all positive. So we're summing all positive height rectangles, if you like. Okay, get the idea. Nice and tricky if you're allowed to use technology. Some questions won't allow you to do that. And also, it will not give you the exact answer in root 2s and things. It'll change it to a decimal. Here it's okay, it's a whole number. But if they say find the exact answer, you can't use the calculator like that. Okay, well, I guess you know what's coming up now, and that's to do it in graph mode. Let's see what it does. It's interesting. So start with graph mode, hit execute. Here we come to this window, and now we have to put the function in. So here, what we need to do is to put in abs. So we've got to find abs in function mode. So you go to options. Here we are, options, which is F2. And if you do that, you get this screen here, number. So you have to hit number this time in graph mode, and that's F5, and you get abs sitting in there. Okay, so you've got to put the abs in here, and then you can put the function in. When abs comes up, the absolute value sign, put the function in. So just watch that. Absolute value occurs in a different place here in graph mode. You've got to choose options and then go to number and get your abs out of there, where it's complex. In run mode, you've got to find the complex button there. Okay, so then you draw the graph and see what it's done. It has, instead of doing a proper sine 2x, made that positive, and it sits up there. Okay, so come over here, and what we now do, now we're in graph mode, we can do shift, and I've done this, shift F5 to G-solve in there. G-solve up the top. And if you go to the second window, there's the integral sign. In G-solve, it's the second window there, like we did before. And then we are asked for lower, here's our window here, if you execute that. Lower is naught, execute it. Upper is pi, and all it shades it in. And we can see everything's cool. Notice that if we didn't do abs, it would shade in this, and the answer would be 0, showing you where it's done the calculations of an infinite number of rectangles, but it would come out to nothing, wouldn't it? Okay, because one would balance them out. This would be negative rectangle heights times delta x. This would be positive, overall answer 0. To be a bit in trouble there. Okay, so this graphical way just shows you that everything's up the right way, if you like. Okay, you need to have this technology, so try to remember that, write some notes down on how to do that. Okay, so let's have a look at this answer here, and to this question. Okay, find the area enclosed by one arch of y equals sine 2x. Okay, so here, to find one arch, you need to know where that stops, and that's at pi on 2, because sine of pi on 2 is, sine of 2 times pi on 2 is sine of pi is 0. So we've got to determine that. So the first positive x-intercept pi on 2. So we go from 0 to pi on 2 of sine 2x. Here, is that a derivative of a function? Yes, neg cos 2x, but we have to divide by the derivative of this. This is actually a function of a function. So the chain rule will have us times by 2. We've got to reverse that and divide by 2. A linear example of the chain rule here. Okay, so 0 to pi on 2. Put it in our new notation. Substitute it in pi on 2 there. 2 times pi on 2 is pi minus cos of 0. Cos of pi is neg 1. Cos of 0 is 1. So it's neg 1 take 1. Is neg 2 times a half is 1. So it's coming out nice and positive as we would expect. Positive rectangle heights there. Okay, come down to 7d4. And it's a show that. So show that, you can't use technology here. So you've actually got to check the graph out and set it up as an integral from 0 to pi and have a look at that. So I would just check the graph. You have to have an idea of the graph, and then you could check it with technology, just to make sure your skills are there. And here we are, the area enclosed by y equals sine squared x. Now that's not a show that, so you could go straight to the calculator for that. Or you could draw the graphs, check where it's going above or below the axis and split the interval. But this is a candidate for absolute value of sine squared x on the calculator, isn't it? Where the calculator takes care of any problems with the negative area under the curve. Okay, so there's some interesting ones here. Just think about what you're doing. That's very, very important. And things like down here, find algebraically and find the total area. You could use the calculator for this, but you can't use the calculator for that because it says find algebraically. So play around with all these things and see what you come up with. Okay, so let's go back now and just pause it there and have a go at those three problems. And then I'll bring it down and then we'll look at the solutions. Okay, so 4, 5 and 6 then. Okay, and then the answers here are there. Okay, so check those and see what you think. All right, let's come to the last little bit now. And here we are. Use your graphics calculator to find sine of root x. And the rest of them here, you look at this and you say, can I actually have a function which has this as a derivative? No, so that's why they've said to actually use a calculator, okay, for each of these. So the calculator can do it for you where you haven't got the skills yet to do the integral of any function, for example. Okay, the calculator use other methods. And we'll be looking at that in a later presentation in solving differential equations. Okay, so here, have a look at each of them. You can use the calculator for this one, and I'll just show you the answers then. There we are. All right, so I hope you're building up some skills and got some strategies for handling these problems. And well done for getting to this point. Keep up with it. We've got a couple of more presentations to complete the course, and then you've graduated. Cheers for now.